Hello and welcome to this lesson where I'm going to teach you how you carry out calculations that involve the YouTube. Many times I've seen that this is one of the areas that gives students a lot of problems. So what are some of the things you can learn once and for all that are going to help you with this type of question? I want to start with a situation where you have to calculate pressure at a point in a liquid. So over here, I have a beaker, which is of course open to the atmosphere. And in that beaker, I've got a liquid, say water. I want to calculate the pressure at the bottom of that liquid, which is water. Many times you find that when students are given this question, they always use the equation rho hg. Rho is the density of water, h is the depth of the surface, is the depth of the point from the surface, and of course g is the gravitational field strength. But they forget that the atmosphere also exerts a pressure at that point. So pressure at the bottom of this container is due to two fluids. Number one, atmospheric pressure, and pressure due to the liquid column, which is rho hg. So, unless the question is specifically asking you to calculate pressure in excess of the atmosphere, unless the question is specifically asking you to calculate the pressure at this point in excess of atmospheric pressure, you should bear in mind that when you ask that question, it must involve the pressure due to the atmosphere. So if the question is stated like, calculate pressure at the bottom of the container, which is in excess of the atmosphere. In other words, the difference between the pressure at the bottom and atmospheric pressure, how much is it? But if the question is very plain, it's asking you to calculate pressure at the bottom of the container, always realize that that pressure must include atmospheric pressure. So the correct way of calculating the pressure at the bottom of the atmosphere is by saying pressure at the bottom of the container is equal to atmospheric pressure plus rho hg. With that one in mind, let's look at the manometer, or what we call the U-tube. It's referred to as a U-tube because first of all, it looks like the letter U. But you can make one in the lab. How? Get two burettes and then connect them with the rubber tubing. Of course, make sure that they are those burettes and the tap is completely open. And then you can have your U-tube. And then inside those glass tubings, you're going to put a liquid. Let's say mercury. But mercury is no longer used in high schools nowadays because it is toxic. So this experiment can only be done under close supervision by the teacher as a demonstration. So let's assume that that is the situation that we have. I'd like you to note that the moment these two arms of the burette, they are open to the atmosphere, it tells us that atmospheric pressure is acting on this surface, and also atmospheric pressure is acting on this surface. And notice that this one is a continuous liquid. The liquid on the left-hand arm is in contact with the liquid on the right-hand arm. As a matter of fact, if we apply some gas pressure here, this liquid will move down and this one will move up because they are connected by the same fluid. It's continuous. Now, I want to dwell on why the two levels or the two surfaces are on the same horizontal level. They are on the same horizontal level because pressure on this surface is exactly equal to pressure on this surface, which is atmospheric pressure. That is why they are on the same level. What will happen if we pour some liquid into this arm, for example? Let's assume we pour some water in it. What will happen? This is the situation. The moment we pour another liquid, say water, the pressure on this surface here will no longer be atmospheric because another liquid has been poured in. So that liquid must increase the pressure on the surface of the mercury. So how much is the pressure on this surface? It will be atmospheric pressure plus pressure due to this water column. You can see that the pressure on this surface has increased. It's more than atmospheric pressure, and therefore that surface is going to push the other surface up. As it moves down, the other surface will move upwards. And that is exactly what happens here. If we increase the amount of water in it, this level will continuously move down while this one continuously rises. Why does that happen? It happens because the pressure on this mercury surface is increasing with more addition of water on this other side. While the pressure on the mercury surface on the other side remains atmospheric because the only fluid above it is the atmosphere. So what do we do in this case? We always draw a line. Draw a horizontal line at a convenient point. And in this case, I would choose this to be the convenient point. I'm going to explain later why I do that. But the moment I choose this, I'm going to note that that point there, I'm going to call it point A. And I also identify a point on the other side, which is on the same horizontal level with it. And then use this statement. Since point A and point B are on the same horizontal level, then it implies that pressure at point A is equals to pressure at point B. And that is what I quickly write here. Pressure at point A is equals to pressure at point B, like that. And then I ask myself, what fluids do we have above point A? One of them is the atmosphere. Notice that both arms of the U-tube, they are open to the atmosphere. So atmospheric pressure is acting on the water here. So I'm going to say one of the pressures is pressure due to the atmosphere, PATM. I'm going to use that short form or that abbreviation to stand for atmospheric pressure. Then the water, whose density is ρ1, is exerting pressure at that point too, and its depth from that surface is this much. Excuse my crooked line over there. So I'm going to call that one H1. So I'm going to have ρ1, which is the density of the water, H1, which is its vertical height, times G. Those are the only two fluids above it. When I go to the right-hand side, I can see that one of the fluids exerting pressure at this point is the atmosphere, PATM. PATM. Of course, over here, the PATM was also there, because I do not want you to confuse this with what I've written here. What I've written here is actually this one here. So we have P due to the atmosphere, plus there is this H here due to the mercury column, H2, because this density here is ρ2. So it is atmospheric pressure plus ρ2, H2, G. And you can see, if I subtract PATM from both sides, it disappears. And I have ρ1, H1G is equals to ρ2, H2G. And the G's cancel out, and I get a very simple expression. ρ1, H1 is equals to ρ2, H2. By using that expression, I can be able to calculate the density of one of the liquids if I measure the heights. But notice the trick. I had to start with a point where I drew a horizontal line that cuts out, that helps me to say pressure at this point is equals to pressure at this point. Now, let us see what happens when we introduce another liquid. into the right hand arm. I've already looked at a situation where I introduced one liquid on the arm on the left, which is this one here, and this one rises while this one falls, and it allows me to calculate the density of any one of those two liquids. Let's now look at this situation here where I pour in water to the right hand glass tube. And you can see that the moment we do that, this level is going to drop slightly while this one must rise. The reason why this one drops slightly from where it was, because it was here, now it has dropped to this point here, is because the pressure on this liquid surface here, mercury surface at this point, has increased. And therefore, since it has increased, this level drops while this one rises slightly because the one on the left remains constant. So what kind of expression am I going to get? I need to know the point where to draw my horizontal line. For example, I can draw my horizontal line here, or I can even have it here. If I have it here, I'm going to have pressure due to the atmosphere plus ρ1 h1g. In this case, I'm measuring my h from here all the way to this point. So ρ1 h1g is equal to pressure due to the atmosphere plus ρ3 h3g plus ρ2 h2g. Because mercury, I'm going to give it the density, the density ρ2. So this is ρ1, ρ2, ρ3, and of course we've got the atmosphere. What will happen when we increase the quantity of the orange liquid? Let's see what we get. We have increased now the quantity of the orange liquid. Remember, the mercury level was here. The moment we increased it, that mercury level drops down. So we can carefully increase that liquid until this mercury level goes back to where it was in the beginning. Here. This one goes to where it was in the beginning, and this one comes back from here to where it was in the beginning. That gives us a very simple expression and a very convenient point about which we are going to consider the pressure. For example, the most convenient point in this case to draw a horizontal line is this point here and this point here. I'm going to say, let's consider this point to be point E and point F. Like that. And we're going to say, since point E and point F are on the same horizontal level, then pressure at point E is equals to pressure at point F. Pressure at point E, one of them is pressure due to the atmosphere, so P ATM plus ρ1 h1g. Where is our h1? This is our h1. So since this is our ρ1, our h1 is from this point all the way to this point. Again, I want you to excuse my crooked lines here. This is our h1. And our h3, because the orange liquid has got density ρ3, so this must be h3. This is ρ3. So this one is going to be equal to pressure due to the atmosphere, P ATM, plus ρ3 h3g. We can be able to show that ρ1 h1 is equals to ρ3 h3. In most examinations, you're just required to recall this expression. Not much is expected. Just recall that particular expression. But that does not stop the examiner from giving you a complicated question like this, where you're going to say, okay, I'm used to a situation whereby mercury on both sides, they are on the same horizontal level. Now they are not, and I don't know the point about which to draw my horizontal line. You can draw your horizontal line here in which case you are now going to consider the atmosphere, water, mercury, this liquid, and the atmosphere. Or the common situation is where they increase the level or the amount of this liquid, one of these liquids. They can either decrease that amount or increase this amount, depending on which level is higher than the other. So in order for us to bring this level to be the same as, on the same horizontal level as this one, there are two things that you can do. Either we can decrease this quantity, in which case the pressure here is going to reduce, allowing this level to rise, and simultaneously this will start to drop. Or we can increase the quantity of this liquid here, in which case the pressure here is going to increase, making this level to fall and this one to rise. So what I did in my example is to increase the quantity of the orange liquid. And that brought the surfaces of the mercury to be the same. So remember, it is not a must that the surfaces of mercury must always be the same. It's always done for convenience and to make the calculations easier. But should the examiner want to make it a little bit complicated, they can do that. So it is important that you learn how this expression has been obtained, because many students use this expression without wanting to know how it had been obtained in the first place. And when it is slightly altered, then they have a problem with using it. I hope you've been able to learn a lot, and I've shared some insight on how to use the YouTube when you're carrying out many calculations. Any calculations that involve the use of the YouTube, you'll find that it makes use of the concept that I've taught you today. Identify that point whereby if you draw a horizontal line, you'll be able to say, and that point must be a convenient point. Pressure at this point is equals to pressure at this point by virtue of the fact that the 2 points are on the same horizontal level. You will never go wrong when you start that way. And when you consider that particular point, you look at all the fluids that are above that point. Then the heights that you use are only the heights for that particular fluid. For instance, when I'm talking about this, the pressure at this point, due to this liquid here, I will say it is this height times its density. I don't use this density and then measure all the height all the way from to that point. No, it is just the height that for that particular liquid. The height for that particular liquid. Yeah. When you use that concept, drawing a line and then using that idea that because the 2 points are at the same horizontal level, then pressure at this point is equals to pressure at this point, and then you go ahead and consider all the fluids above that particular point, you will never go wrong, including situations of where you are being asked to calculate pressure of the gas. How do they do that? They could close one of the tubes. They could close one of the tubes and then ask you to calculate the pressure of the gas inside there. When one of the tubes is closed, then you will have to know that on that arm, you cannot use atmospheric pressure. You use pressure of the gas. For example, if this tube was closed here, you will say pressure of the gas plus rho 2 H2 G is equal to atmospheric pressure plus rho 1 H1 G. Of course, if I draw a line here and this tube was closed to the atmosphere like that. That one is so important. You will never go wrong. The pressure of the gas can be equal to atmospheric pressure, or it can be higher than atmospheric pressure, or even lower than atmospheric pressure. Any one of those situations is possible. If you follow this concept that I've taught you in this lesson, you will never have a problem with any question that involves the YouTube. And I want to throw a challenge to you. Look at as many questions as possible that involve the YouTube and give me that one question which is not working out using those concepts that I've taught you. What are these concepts? I want to make a summary now. Identify that convenient point where you can draw a horizontal line. Once you do that, measure the height of the various fluids above that particular line. Because you are saying pressure at this point is equals to pressure of this point by virtue of the fact that the 2 points are on the same horizontal level. Then consider the pressure due to all liquids or all fluids which are above that point. All of them. Then you go to the other side of the equal sign. Consider all the fluids which are above there. And I can guarantee you that most of them will cancel out, giving you a very simple expression. So to begin with, when you're working out this question, always derive that particular expression. Always derive it so that you can be able to see how it works out. Again, the challenge is to you. Let me know in the comments below if there is any question that you are unable to solve when you apply the concepts that I've taught you today. Otherwise, until next time when I come up with another video where I'm teaching you another concept, it is goodbye and have a good time.